Well, I'd like to welcome you back to our practical problem-solving clinic using experimental techniques. This is part 2 of 5 parts. And in part 2, we'll be discussing testing for means, continue our discussion of type 1 and type 2 errors, introduce tests for proportions. We'll talk about design of experiments and how they work. We'll give you an example of a designed experiment and then move on to an introduction to the analysis of variance. First off, tests of hypothesis, testing for means. A test for means is used to determine if some change to the process has resulted in its mean to shift from the traditional value. And what we're talking about in terms of a change to the process is some kind of variable change, changing a key process variable like pressure from the current status to an alternate status, a different material from the current to an alternate. Now, this test assumes that we have previous information about the process. We have historical data about the mean and standard deviation. Now, if we don't have this historical data, then it's not appropriate to use this test. So here is an example of a test for means. This example is not unusual in that the data has been supported by long-term production in the past. In our example, the average productivity on our production line over the last 6 months has been 800 units per hour with a standard deviation of 6 units per hour. We formed a process improvement team and they've determined that a change to the raw material would improve yield. Although the new material cost is higher, we hope to reduce the overall cost by using the new material. Should we recommend this change to our management? So let's have a few assumptions. The assumptions for this test is that the characteristics we are investigating is approximately normally distributed, that it fills the normal distribution, and that we are able to take random samples, and we know the historic process mean and standard deviation. And we've determined that our sample size can be greater than or equal to 30 without a significant economic hardship or disruption to the production schedule. So we talked about in the last module, we talked about 8 steps. This is step 1, and that is to formulate in words the theory or hypothesis that you wish to test. For our test here, our process has been producing an average of 800 pieces an hour over the last year, and we propose a change to the process by using a new, more expensive raw material. So the question is, can we prove that the extra cost of raw material will be more than offset by an increase in production? So in step 2, we state the theory in statistical terms. Here we're going to formulate the null hypothesis. If you recall, the null hypothesis is the innocent hypothesis. In our example, HO is that mu equals 800 pieces an hour. Mu, if you recall, is the long-term process average. Please note that there are other types of null hypotheses using the greater than or less than relations, but for simplicity's sake, we're going to restrict ourselves to the equal sign in this particular example. Step 3 is to state in statistical terms what conclusions we would reach if the theory turns out to be false. What is the alternative? We write the alternative hypothesis, and that is the HA in that the mu, the new process, is not equal to 800 pieces an hour. Because we do not know if the new process performance will be above or below the historic number, we will test both possibilities, that is, less than or more than the historic average. Step 4 is to set a margin of error for the decision. So this is what the team has to explore. How expensive, how serious are the consequences if we make a wrong decision? Step 5 is to select an appropriate sample size. For simplicity's sake, we will set the probability of our type 1 error, that is our alpha error, at 0.05 or 5%. Since our test requires a sample size of at least 30, and there's nothing indicating that sampling will cost us too much money, we will use N, or the sample size will be 30. In real-life situations, type 1 and type 2 errors would be determined as a result of careful consideration of the ramifications of a mistake. Remember, in the last module, we discussed the ramifications of error in capital punishment. The risk and cost of making an error in capital punishment is very high. It's likely that the decision that you make in your process experiments won't be that high. Your team must determine how much risk cost is acceptable if an error is made. And since this is a classroom exercise, we'll use the common 5% value for the type 1 error. Step 6 is to choose the test statistic and formulate the decision rule. For a single sample test of means with a known standard deviation, the test statistic is Z equals the average, that is the X bar, minus the long-term average, the mu, divided by the standard deviation over the square root of the sample size. In the test statistic, the variables are the X bar, the average of the sample we've drawn from the new process, mu, the historic process average, sigma, the historic process standard deviation, and the square root of n, the square root of our sample size, in this case, 30. If the null hypothesis is true, the test statistic is distributed as a standard normal distribution, and that is mean 0, standard deviation equals 1. So we look up in a normal table, and I'll show you that in a moment, the value for Z equals alpha divided by 2. So we said that we're going to be testing for greater than and less than, so we have to consider both tails of the probability distribution. In our case, Z is 0.05, that's the 5%, divided by 2, and that's 0.025. For Z equals 1 minus alpha divided by 2, and that is 0.0975. So I'll show you how to find those in our table of cumulative normal probabilities which follow. And you can find these tables in many sources, in many books, and I've highlighted 2 that you can find on the web. So we're going to be looking for the lower tail and find the critical Z value. To find that Z score equivalent to the alpha equals 0.025, we'll look through the probability table until we find this probability listed. You look at the graph there, what we're really looking for is the area under the curve that's all the way to the left. We're looking for a Z score. And when we get to our table here in a moment, the left-hand column will find the first 2 digits minus 1.9. Then we'll look across the top row of the table and find the last digit, 0.06. Combining these, we'll get minus 1.96, and that will represent the area under the curve of 2.5%. So we're looking at our normal probability distribution table. This one happens to come from RIT. It's called the Standard Normal Distribution Table. And we look in the table and we try to hunt for a value that is close to 2.5%. In this case, you find the rectangle that I've superimposed on the table. You see 0.02500. And that aligns with minus 1.9 in the left-hand column and 0.06 across the top. Finding the upper tail of our z-score is done in a similar fashion. We'll be looking for the probability of the area under the curve of 97.5% or 0.0975. And we're looking for, in our table, the value 0.97500. Now you may recognize that this table is positive z-scores because the distribution is representing the area to the right of the average. And we look at the table and we find that that z-score is a plus 1.96. Now, a word of caution about normal tables or any tables that you find in a book. There's so many ways that authors create these standard normal tables. Each one is just a little bit different, and they're all correct, but they have to be read in a way that you understand it. And for this reason, it's good practice to become comfortable with one particular table and stick with it. And you'll get that a bit by experience. So our two critical values for the test for a two-tailed type 1 error of 5%, and as you recall, we split the 5% between the two ends of the distribution. In our example, we found the lower critical value to be minus 1.96 and the upper critical value to be plus 1.96. Therefore, our acceptance region, and that is the region that we would say that we would accept the null hypothesis, would be if we find a z-score which is greater than minus 1.96, but is less than plus 1.96. And we reject the null hypothesis if the z-score is either less than 1.96 or if the z-score is greater than 1.96. This would indicate that the mean has indeed shifted. So as you recall, for this test, we did divide the chances of the type 1 error in half to reflect that we are conducting a two-tailed test. We use the two-tailed test to determine if we're interested in knowing if the process is shifted in either direction. The alternate hypothesis would be that the mu, that is the new standard mu process mean, is not equal to the old process mean. A one-tailed test refers to a test which has a single alternate hypothesis, such as mu is greater than, the new mu is greater than the old mu, the initial mu. Step 7 is to select samples from the process and calculate the test statistic. In our previous example, one sample randomly selected from each of 30 hours, that's one sample per hour, of production are drawn from the new process. The values for mu and the sigma are taken from previous data and simply plugged into our equation. We make the decision based on the criteria which was formed in advance of the test. If you recall, we're saying if z is greater than 1.96, we reject the null hypothesis and conclude that the new process mean is greater than the historical value. And in the same way, if our new z is less than minus 1.96, we reject the null hypothesis and conclude that the new process mean is less than the historic value. If the z is between minus 1.96 and positive 1.96, then we accept the null hypothesis and conclude that the process has not changed. The new average is the same as the old average. One more thing. When we say that we conclude that the process has not changed, what we really mean is to say that we have insufficient evidence to support the premise that a change has taken place. We never prove anything with a test of hypothesis because, after all, we're taking samples and we're inferring the truth from the samples. Making the decision rule, as we've discussed several times now, we're looking to understand, will the z that we calculate fall within the acceptance region, that is between minus 1.96 and positive 1.96, or outside that acceptance region? And that's with our standard normal distribution that is represented by those tables that we saw a few slides ago. Okay, we're finally getting to the point where we can make a decision based on the data. Again, if you recall, the old process averaged 800 pieces an hour with a standard deviation of 6. The question is, does the process perform better or worse after the change? Well, we do our sample and we find that after sampling, our new process averages 805 pieces per hour. Therefore, can we conclude that things have improved or not? So in step 8, we're going to be making the decision on our process based on the data. Our test statistic is z equals x bar minus mu divided by sigma divided by the square root of the sample size. 805 minus 800, 805 is the new sample, minus 800, which was the old process average, divided by 6, which is the old process standard deviation, divided by 5.48, which is the square root of 30. That gives us a result of a z-score of 4.58. So since 4.58 is greater than 1.96, we can reject the null hypothesis, and you'll recall the null hypothesis is the innocent hypothesis that nothing is different, and now infer that the process has indeed changed, and good news, it's moved in the right direction. Now bear in mind, since we entered a table and we selected a 0.05 and split that risk on both tails, if you recall, in our probability distribution table, we do have a 5% chance that we made a mistake making this conclusion. How about another example? A manufacturer of sports equipment has developed a new synthetic fishing line they claim has an average, that is a mean, breaking strength of 15 pounds with a standard deviation of 0.05 pounds. We wish to test the null hypothesis that mu, that is the average, is 15 pounds against the alternative hypothesis that mu is not 15 pounds. We select a random sample of 50 lines and we test them and find them to have a mean breaking strength of 14.8 pounds. We choose the risk of making a type 1 error at 1%. Do you accept the manufacturer's claim that the mean breaking strength is 15 pounds? So our first step is to look at our standard normal distribution table, as we did in the last example. But now we're going to be looking for half, since this is a two-tailed test, half of a 1% error. So we look at the table and we find a number that is as close to 0.005 as possible. And we find it in the row 2.5 and in the column 0.08. So our lower critical limit is 2.58, minus 2.58. And looking for the upper tail of the test, we're looking for the upper tail to be half of that 1%. So we find 0.99506 as the closest number to a half of a percent. And of course, it's symmetrical with the lower tail, so this is 2.58 on a positive. In our fishing line example, our null hypothesis is that the HO, that the manufacturer is claiming that the average breaking strength is 15 pounds. Our alternative hypothesis is that mu is not 15 pounds. And we've selected an error rate of 1%, alpha equals 0.01. So by looking into the table in our previous slides, we know that our acceptance region is to find a z-score to support the null hypothesis. We'd have to find a z-score between minus 2.58 and positive 2.58. And we use our test statistic z equals x bar minus mu divided by sigma divided by the square root of the sample size. So our z is calculated by our sample, 14.8 minus 15 divided by 0.5, which is the standard deviation. That's divided by the square root of the sample size, 50. Our calculation is that we find that the z is minus 2.828, which unfortunately falls beyond the critical point of 2.58. And therefore, we have to reject the null hypothesis that the average breaking strength is 15 pounds and conclude that we cannot support the manufacturer's claim. How about another example? A life insurance company is required to update their actuarial tables every 5 years. Their level of risk tolerance of rejecting a business assumption when it is true is 5%. A random sample of 100 recorded deaths in the United States during the past year showed an average lifespan of 71.8 years, with a standard deviation of 8.9 years. Does this indicate that the average lifespan today is greater than 50 years ago when it was 70 years? Just a note, an actuary is a business professional who analyzes the financial consequences of risk. Actuaries use mathematics, statistics, and financial theory to study uncertain future events, especially those of concern to insurance and pension programs. So we look in our standard normal table, and we're looking for that 5% error, and we find 95. So this is going to be a one-tail test. So we're looking for 95% on the upper tail. You find that in that rectangle. So our critical z-score is 1.65. So in our life insurance example, our null hypothesis is that the average lifespan in the United States is 70 years. Our alternative hypothesis is no, that the average age is greater than 70 years. We've selected an error rate of 5% and looked at the table, and we found that the critical region, or the critical point, is z is greater than 1.645. Using our formula that we've used several times now, we find a calculation of 71.8, which is our new sample size based on sampling 100 deaths in the United States, minus 70, which was the old, if you will, process average, the old historical lifespan, divided by 8.9, which was a historical standard deviation, and that was divided by the square root of 100, which is our sample size. Doing that calculation, we find z equals 2.022, which happily falls beyond that critical limit, which says that our lifespan has indeed increased, and therefore we can no longer support the null hypothesis. We reject the null hypothesis and conclude that lifespan today is greater than 70 years. So we've talked about testing for means. How about testing for proportions or percentages. So testing for proportions or percentages. It is sometimes necessary to test the idea that a change has occurred in a process characteristic that is measured by attribute data, counts, or percentages rather than in variable measurements. For example, scrap rates percentages, percent on time shipments, absentee rate percentage, process yield percentage, sorting rates, and so forth. So in a test for proportions, the null hypothesis is that the HO is that P, which is the new process, equals the original process. In words, this means that the new proportion or percentage is the same as the traditional value. Some examples. The percent scrap for the new process is equal to the percent scrap of the old process. The percentage of on-time shipments is the same now as it always has been. The change to our attendance policy did not affect the rate of absenteeism. And the yield of our injection molding process is the same since we changed to a new supplier. These are all hypotheses that we might want to test. The alternative hypothesis is that the percentage or proportion is not the same. It's either greater or less than the previous process. For example, the scrap rate after our process change is less or more than the old scrap rate. The percentage of on-time shipments increased or decreased after a change in the standard operating procedure. We have more or less absenteeism than we did before we made a change in our attendance program, or the injection molding yield got better or worse with the new supplier of resin. The alternative hypothesis. Some assumptions. First, that the individual trials are independent. This means that the results of one trial have no bearing on the results of the next trial. They are independent. In addition, the process must be operating randomly and must be in the state of control. If the process is bouncing all around and out of control and unpredictable, then we really can't be testing because it's a fool's errand to be testing a process that's out of control. And that our sample size is large enough so that we would expect to see, on average, at least 5 defects in each sample. So how many samples should you take? Well, I've used for many years a sort of rule of thumb that says the sample size should be large enough that on average you'd find 5 defects or 5 non-conforming in every sample. Example, if our process is averaging 5% defects, using this pretty simple formula, 5 divided by P bar, the average fraction defective, 5 divided by 0.05 would mean that the minimum sample size you'd want to take is 100. How about a test for proportions based on the Dow Jones Industrial Average? The Dow Jones Industrial Average, or the Dow, is a stock market index many investors use to gauge the growth of the stock market investments. The Dow shows how 30 large publicly owned companies based in the United States have traded during a standard trading session. The question is it more likely to go up more than it is to go down? So I graphed 5 days in March 2015 and then 5 years prior to March 2015. And you can see in the short term, in March 2015, there was quite a bit of variability. But in the 5 years prior to March 2015, that variability seems to smooth out, and you look for it looks like a nice long-term trend up. So in our Dow example, we're going to formulate in words the theory or hypothesis that we wish to test. And that is the Dow just as likely to move higher as it is to move lower on any given day? So our null hypothesis is HO, that the PO equals 0.5, just as equal to go higher as it is to go lower, where P is the proportion of days on which the Dow increases. Step 3 is to state in statistical terms what conclusion we will reach if the theory turns out to be false. And that's the alternative hypothesis, the HA, which is that P0 does not equal 0.5. So steps 4, 5, and 6 in our Dow example. Step 4 is where we're going to set a margin of error for this decision and select an appropriate sample size. The type 1 error that we're going to select here is 5%. Now, out of the 1,112 trading days between 1982 and 1986, the Dow Jones average increased on 573 days. Therefore, the sample proportion is 0.5153 or 51.53%. We're going to write down this test statistic and the decision rule. And on the right, you'll see our Z calculation that we're going to use. So we look in our standard normal table, and we're looking for that one-tailed test, 0.95053. That's as close as we can get to 95%. And we find that that is our Z factor is 1.65. So our decision rule for this example is, if you recall, that the level of error that we're accepting is 5%. The alpha level is 5%. We found that in the normal table as a Z factor of 1.65. So we're saying that we're going to accept the null hypothesis if the Z is lower than 1.65 and reject the null hypothesis if it's greater than 1.65. So step 7 is to draw and measure the samples and calculate the test statistics. So if we plug the numbers into our formula that we showed you in a previous slide, we find that our Z number for this particular sample is 1.02. So step 8 is to make the decision based on the criteria which was formed in advance of the test. We've calculated our test statistic, and now we can make a decision. Since the value of the test statistic, 1.02, did not exceed the critical value of 1.65, we accept the null hypothesis and conclude that there is insufficient evidence that the percentage of days the Dow goes up is more than 50%. As represented by our little graph, our acceptance region is the area to the left of our critical value, 1.65, and our actual calculated test statistic is 1.02, so therefore we accept the null hypothesis. How about another example for proportions? Arthritis is a painful chronic inflammation of the joints. An experiment on the side effects of pain relievers examined arthritis patients to find the proportion of patients who suffer side effects when using ibuprofen to relieve the pain. If more than 3% of the users suffer side effects, the FDA will put a stronger warning label on packages of ibuprofen. Step 1. We're going to formulate the hypothesis in non-mathematical terms. Will the FDA require a warning on ibuprofen? Step 2. We're going to state our null hypothesis, and that is that the P0 is 0.03, that's 3%, where P is the proportion of users of ibuprofen who do suffer side effects. Our alternative hypothesis is that the P0 is greater than 0.03, greater than 3%. So now we'll proceed to steps 4, 5, and 6. In step 4, we'll select our type 1 error to be 5%. Step 5, we'll calculate the sample size. We have 440 subjects with chronic arthritis, and they were given ibuprofen for pain relief. Of those 440 subjects, 22 of them suffered from adverse side effects. So our sample proportion is 23 divided by 440, or 5.23%. So our decision rule for an error rate of 5% is found in the normal table. We've looked at that normal table before, and we find that we can reject the null hypothesis if z is greater than 1.65. Otherwise, we'll accept the null hypothesis. So on our pain relief example, steps 7 and 8. Step 7 is that we're going to draw and measure the samples and calculate the test statistics. Well, in a previous slide, we've already selected the samples and calculated the proportion, if you will, with adverse effects. We'll plug the numbers into the formula, and we'll make the decision based on the criteria which was formed in advance of the test. So when we put in the numbers in the formula, we find that our z factor is calculated as 2.75. Since the value of the test statistic, 2.75, is beyond the critical value of 1.65, we reject the null hypothesis and conclude that there is sufficient evidence to conclude that the proportion of ibuprofen users who suffer adverse side effects is greater than 3%. Again, using the little graph, our critical value for this test, this one-tailed test, is z equals 1.65. Our calculated z value was greater than 1.65, so we reject the null hypothesis. Just a few comments on the examples. Note that in the Dow example and in the fictitious pain relief example, these were both illustrations of a one-tailed test. In general, hypothesis tests can be run as either a one-tailed test or a two-tailed test by adjusting the alternative hypothesis and the critical numbers accordingly. So let's move on to section 3, designed experiments and analysis of variance. So in section 3, we're going to be discussing designed experiments. A DOE, or designed experiments. We're going to be talking about the advantages of using designed experiments, how they work, some basic terminology. We're going to be introducing analysis of variance, ANOVA, types of designed experiments, introducing Taguchi and his Taguchi experiments, and specifically the L4 Taguchi and L8 designs. Designed experiments. A bit of a definition. The work of a designed experiment is the effort to improve products, processes, and outcomes with controlled experimental methods. Designed experiments can be used to systematically investigate process or product variables that affect product quality. Teamwork and formal planning are used to investigate variables of interest and their level of impact made on products, processes, and outcomes. Design experiments are not done on your own, are not a trivial effort, completed in the office, performed in a hurry, or a random process. DOE is a structured approach to problem solving that allows us to study multiple process variables at the same time. DOE is an efficient form of experimentation because it provides reliable results in less time and at lower cost. Use of designed experiments allow us to extract even complex relationships between variables. How DOE works, the basic concept, and more on terminology. How about an example? Suppose we are interested in studying the effects of a proposed process change for a machine that cuts stainless steel tubing to length. The tubing is used to manufacture components of an automotive exhaust system. So the characteristic we are interested in is length control. This example is about length control, an experiment about length control of automotive exhaust tubing. So you can see on the right-hand side a cutting machine. The tubing that you see being pushed through a set of clamp dies is fed by pushing or rolling feed rolls. Those are the orange items sort of in the background. As the tubing comes through the dies, the tubing hits a feed stop and the dies close, clamp onto the tube, and the cutting blade comes through horizontally, slicing the tube to length, and then the process starts again. So we meet with the tube cutting team, the operators, maintenance, supervisor, and engineering, to get their idea about how to improve the process. And they've agreed that the quality of the length of the tube cutting process is determined by 4 process variables: A, feed rolled compound; B, feed speed; C, roll pressure; and D, die clamp pressure. Some terminology: experimental factors, factor levels, and response variables. An experimental factor are those process variables used in the experiment. In our case, roll material, feed speed, roll pressure, and clamp die pressure. The factor levels are the different settings for each of those process variables. And the response variables are the output responses or the results gained during the experiment. So we want to improve the tube cut length control, and our team has recommended that we test new settings for the 4 process variables against the current settings. So we put together this little table. Our feed roll compound presently is hard, and they're recommending that we go to a softer one. Feed speed is presently fast, and they're recommending that we slow the process down. Roll pressure is low, and they recommend that we go high pressure. Die clamp pressure is low, and again, they recommend that we increase the die clamp pressure to high. So since the tubing cut lengths for this experiment are measured against a target, we've set up a length gauge which indicates the perfect length as a value of 0, and all other lengths show as a plus or minus from the target. And suppose for the moment we start our experiment with a perfect process, a set of 16 measurements that are all zeros. So for the purpose of this example, we've started with 16 perfect measurements. And just for reference on the subsequent slides, I've included our little matrix of 4 variables and at 2 settings for us to keep track of things. So on our first test, we're going to change factor A, that is the feed roll compound, from hard to soft. And we find that when we change the roll material from hard to soft, it increases the length of the tubing by 2 millimeters. So it's shown in the right. Factor A1, no change. Factor A2, the soft rolls, it changes the length grow by 2 millimeters. So in the second step of the experiment, we're changing the feed speed, factor B, from the current setting, which is fast, to slow. And the effect we find is that it decreases the tube length by 6 millimeters. And that's shown in the blue boxes on the table. The A1, B2s all go down by 6. And the A2, B2s, they all go down by 6. In our next step of the experiments, we change roll pressure from low to high. Just like in our little matrix to the left, our roll pressure goes from low to high, which has an effect of increasing length by 4 millimeters. So that's factor C, C1 and C2. C1, that is low, no change. C2, we increase length by 4 millimeters. 4 millimeters are added to each length in the box. Next, we change clamp pressure from low to high, which decreases length by 2 millimeters. Factor D, clamp pressure, goes from low to high. So here in the matrix, D1 to D2, when we're at the two levels, we decrease length by 2 millimeters. So the numbers in the blue box are all reduced by 2 millimeters. So here is our results, and the question is, can you see a recognizable pattern in the data? The answer is no. So we've gone ahead and established this experiment, and we started, if you recall, with a set of numbers that were all identical, all zeros. And we layered the effects of 4 variables changes on the process to arrive at an apparently random set of values with no apparent pattern. Lots of effort and no good results. In statistical problem solving, we work in just the opposite direction. We start with a random condition and try to get back to the initial condition of the process. And I'll show you that in a minute. So design of experiments is a technique that actually reverses the process that was produced the variation in the previous table. By following a series of simple arithmetic steps, it is possible to separate the effects of the various factors and return to the original data. So we're going to illustrate how to separate the effects of the variables. You recall our table, which seemed like a group of random variables after the 4 process changes. If we look at the columns A1, B1, and add up that column B1, 0, minus 2, 4, and 2, the sum of that is 4. A1, B2, minus 6, minus 8, minus 2, minus 4 is minus 20, and so forth. So we consider the average value at A1. We take 4, which is the sum of column A1, B1, plus minus 20, which is the sum of A1, B2, and divided by 8, which is the number of individual measures, we get minus 2. So that's the average value at level A1. That's feed roll compound setting hard. In a similar fashion, the average value at A2, that is feed roll compound soft, is 12, which is the sum of column A2B1, plus minus 12, which is the sum of column A2B2, divided by 8, those are the number of individuals in the test, equals 0. So the average effect of changing the roll material from hard to soft is A2, the average of A2, minus the average of A1, which is 0, minus 2, which is 2. So the average effect of changing the roll material from hard to soft was 2 millimeters. So these are called main effects. As demonstrated in the previous slide, the effect of changing roll factor A from hard to soft is an addition of 2 millimeters to the length. This value is known as the main effect of variable A. The same technique could be used to show the effect of changing factors in the tubing cutting examples of factors B, C, and D. In addition to main effects, another kind of effect is sometimes present in an experiment. These effects are called interactions. Interactions, in some cases, are difficult to deal with and hard to interpret. Example, suppose 3 drugs are available for treating a certain ailment. We wish to know which drug does the best job of alleviating the illness. So we arrange for an experiment where we either administer the drug, level 2, or not, level 1, to a number of sick people. If no interactions are present, the effect of the drugs is said to be additive. For example, taking drug 1 helps a little, taking drug 2 helps a little more, taking drug 3 helps even more. This is the simplest effect we can hope for and makes analysis of the experiment easier. However, if a drug interaction exists, taking drug 1 and 2 and 3 separately may help, but taking them in combination may make users ill. The effect is not additive, and an interaction exists, and it's very important for us to know about interactions. An interaction is a situation where the effect of one factor changes depending on the level of another factor. They're not independent. Some more terminology. In real life, there are rarely perfect processes that start with zero variation. A certain amount of variation is present in the numbers before we change the settings of the factors. The variation present in the data after we remove the effect of all the variables is called residual variation or leftover variation. Residual variation is sometimes referred to as experimental error. In most experiments, the importance of the main effects and the interaction is judged against this residual or inherent variation. Residual variation can be reviewed as the amount of variation in our process if no changes were introduced. This variation is inherent and it's normal. So why don't we take a little pause and summarize what we've learned so far. Designed experiments greatly improve the efficiency of problem-solving studies. And that is, designed experiments, or DOEs, work to separate the variation we are studying into structured categories, which can then be related to certain variables. DOE results are more reliable because they look at all the combinations of the factors and their levels. Next section, section 3.3, analysis of variance. We're going to be talking about the general concept and use in DOE. Analysis of variance. Once a designed experiment has been planned and run, it's analyzed using a technique called analysis of variance, or ANOVA. ANOVA is a statistical method that determines if a process mean has shifted by looking at the variance. A little review of descriptive statistics. The population or process distribution is described by certain parameters. Normal distributions are defined by their mean, that's the center of the distribution, and by their standard deviation, which describes the width of the distribution. The variance of a normal distribution is defined as the square of the standard deviation, usually noted by sigma squared. Standard deviation squared is the variance. The variance of a process can be estimated in a number of ways from the same data. The general formula is the variance is the sum from n to I of x minus x bar squared divided by n minus 1. So the variance is the average of the squared deviations of the individual data from their mean. In ungrouped data, such as a simple list of measurements, there's only one way to estimate the variance. In group data, such as generated in a DOE, there are a number of ways to estimate this number. Consider our four-way table the table of the tube cutting process that we discussed in the last section. We can estimate the variance in several ways. The variance can be estimated using the dispersion within each factor, A, B, C, and D, and we'll show you how to do that in the next slide. The variance can be estimated using the dispersion between factors, and the variance can also be estimated using the residuals or experimental error. We can estimate the variance within a factor. If you consider the table and take a look at the two columns below A1 and add up each one of those 8 items, 0 plus minus 2 plus 4 and so forth, the sum will be minus 16. In the same way, if you take a look at the two columns below A2, you'll find the sum of that is 0. The average of A1 and A2 is minus 16 plus 0 divided by 16 because there are 16 individuals in the sample set. The average for A is minus 1. We're going to need that minus 1 in our formula for the variance below, because the concept of the variance is that we're going to take each one of the individuals and subtract it from the average and square that and divide that sum by n minus 1. That's the variance. In DOEs, 2 or more estimates of the process variance are made from the group data using different methods. The estimates are made in the ratios by dividing one variance by the other. If both estimates come from the same normal distribution, this ratio forms a known distribution. This is called the F distribution, and we know the range of values it should cover. Assuming the process is distributed as a normal distribution, the ratio of the two variances calculated from independent samples drawn from that population will be distributed as the F distribution. In practice, the F distribution is found in a table of values at the back of any statistics books or on the internet, and there's 3 examples that I've fished out of the internet that you can look at yourself. So the technique that is used to calculate the various estimates of the process variance form certain ratios of different estimates, then compare those ratios to the standard values in an F table is called the analysis of variance, or ANOVA. It is the method used to analyze designed experiments. ANOVAs are a test of hypothesis which utilize a test statistics which is based on the F distribution. The null hypothesis is that the various treatment values do not change the process. That is, that the average of A equals the average of B, which is the average of C, which is the average of D, which is equal to the original. That is the null for factors A, B, C, and D. Everything's equal. That's the null hypothesis. So we find the critical value. Critical value for an ANOVA test, like other tests of hypothesis, is based on a chosen type 1 error. If we choose an alpha of 5% as before, the F value must come from a table for F.05, which I show on the right. If our calculated F value exceeds the critical value of F.05, we reject the null hypothesis and conclude that the means are not all equal. Rejecting the null hypothesis means that the alternative hypothesis is true. So tables for the F distribution are a bit different than others, different than the standard normal table distribution that we spoke about in hypothesis testing. The tables depend on the sample size of the variance in the numerator, of the ratio of variances and the sample size of the variance in the denominator of the ratio of variances, and the type 1 error of the test you selected. So you'll note that instead of sample sizes, tables will usually ask for DF, or degrees of freedom, which you'll recognize to be n, or the sample size, minus 1. So using an F table. So we're going to calculate the variance 1 and the variance 2 from the data. And we're going to divide variance 1 by variance 2. And we're going to find the degrees of freedom for each variance by subtracting 1 from the sample size. Degrees of freedom n1 minus 1 equals the degrees of freedom for the numerator. Degrees of freedom 2 is n2 minus 1 is degrees of freedom for the denominator. Variance 1 divided by variance 2. So we enter the F value for alpha 0.05, or whatever value you have chosen for the type 1 error, and using the degrees of freedom for the numerator, df1, and degrees of freedom for the denominator, df2, we're going to select the critical F value. So let's give this a try. Let's use the table to determine the critical F value for alpha equals 0.05 with variance 1 of degrees of freedom 5 and variance 2 with degrees of freedom 10. We can see that across the top, 1, 2, 3, 4, 5, column 5 degrees of freedom in the numerator, and across the side on the vertical axis, degrees of freedom of 10, and they intersect at 3.326. That would be the degrees of freedom for variance 1 with degrees of freedom of 5 and variance 2 with degrees of freedom of 10. What would be the critical value of alpha if it was 0.01 or 1%? That would be 5.64. It's a different table. Critical values of F for 0.01 or 1% significance level. Degrees of freedom 5 in the numerator. Degrees of freedom 10 in the denominator. 5.64 is the critical value. So in summary, designed experiments are analyzed using a technique called ANOVA. The ANOVA is a test of hypothesis that determines if the process mean is shifted by one or more of the experimental factors or if the mean remains unaffected. Our test statistic for this test is based on the F distribution as made up of the ratio of two independent estimates of the variance. Thank you for your work so far. Please proceed to our next section of practical problem solving using experimentation techniques, part 3. But before we go on, again, credit to the Greater Detroit section of the American Society for Quality for introducing me to hypothesis testing, and to the Ford Motor Company and their work with the American Supplier Institute, Genichi Taguchi and Yuan Wu, in their introduction of offline quality control, and to my colleague, Mr. Tom Dold, for his enduring work in training and continuous improvement. Thank you.